Hi Mason, hi Salim, hi Steven, hi Anchao.
Hi, Professor Steve.
Hello, Professor.
Well,
Yes, hello.
yeah, nice seeing you. Let me see who else is joining. Hi Johan.
Oh, hi, Dr. Kelly. Morning.
Good morning. Yeah, nice hearing you. So we are waiting for Amir and Mahek if they decide to join. So, is it correct that coming Thursday is there are no classes? Does anyone know is if on the Thursday we have meeting or it is officially cancelled because of Easter? So today is 7th and the Thursday will be 9th. Well, I will double check and I will probably connect, but since there is probability, there is a chance that coming Thursday will be a part of the Easter celebration, and there will be no formal class. I suggest that we organize the presentations not on the coming Thursday of April 9th, but the next Thursday, which will be April 16th. Does anyone objects, or it sounds okay?
You mean 2 week next, right?
Yes, presenting the skills of running VASP software not in 2 days but in 9 days on April 16th.
Okay, I have nothing during this quarantine to do. It's okay.
Okay, well, I hope this will give you additional chance to.
Oh no, I'm talking about I don't have any plan for traveling. No, but for educational we have.
Pardon me?
Nothing. I just kidding.
or maybe find a day that's not Tuesday or Thursday, so that we still have like meeting, and then maybe like a day on the weekend or something. I don't know. I'm just
For presentations or for consultation?
for the presentation.
Oh, I understand you have schedule conflicts, but the online connection is facilitated by university, and it is set up for specific dates. So
I see.
And Thursday, I think coming Thursday would be great, but maybe if you have, we all have 2 Wednesday labs before this presentations, then your knowledge will be stone strong and there will be benefits.
Yes, that makes sense.
Okay. So so we are presenting on April 16th, and on midnight of Wednesday, April 15th, I will look forward to receive slides of your presentations. The plan is, I think the best arrangement, if you send all your presentations to me, and I will be projecting them same way as we project the slides of the lecture, and whoever is a speaker will just tell, like, next slide please, because if each of attendees will try to share screen, it will be a lot of delays due to technical aspects. So if anyone objects this plan, you can speak now or send me an email later, but I suggest we go this way. Okay, so today's meeting will be quite brief because I'm trying to expand original lecture number 21 into 22 and 23, so make it 3 times slower. And we are ahead of the plan with lectures, and we are behind plan with labs, so it will be justified. So let me scroll through the slides. So the slide set is the same as I was sending last time. I will just cover last half dozen slides today, and maybe make a little review of the same things we did before. So the presentations which we just agree to perform on April 16th are very close, well, they're coming close to completion. So the UV-Vis spectra were partially covered in the last lecture, and it was also covered in the homework that everyone is welcome to send if you didn't. I wasn't checking email like half an hour before the lecture, so there are just a couple of individuals who submitted, but it's preferred, but if you want to postpone it for a couple of days, it is okay. So we'll start the coming lab from the recital of this subject. And the next subject that will be, because we will have 2 labs more, the next subject that we will definitely cover tomorrow is thermal heating and movies. So the density of states, spectra, and molecular dynamics are 3 minimal critical things. And then as we go, maybe we will cover the remaining things also tomorrow, but I will use them as the backup for end of tomorrow's lab and for the lab before the presentations. So I am very much open for any email questions about the subjects, especially the subject of the spectra, so that we were recalling last time. So we all are computing this transition dipoles, and they're used for computing the absorption spectra. So images like this are were submitted by those who submitted the homework. So in the lecture that we are expanding for a little longer than originally planned, we are pursuing the following goal. By now, you all are aware of theorems, why density functional theory works, and by our collective effort in a couple of classes before. We all got the idea how the software is working for computing electronic structure. So it is also part of the homework that you are completing. There is a flow chart. The goal of the DFT is to provide the total energy, and it uses an auxiliary concept of total charge density, which we compose of the occupied orbital squared. And orbitals are obtained by extracting the external potential for auxiliary world where electrons do not interact from the total energy. And those equations for orbitals in the auxiliary world can be chopped by separation of variable from one equation for many electrons to individual equations for one electron. So those equations are so-called Kohn-Sham equation. In practicing this self-consistent procedure, which also uses the background mean field and self-consistent procedure, same as a Hartree-Fock, one does need a connection between density and total energy. When we were just starting this chapter, we have touched the so-called Thomas Fermi theory, and now we are making an example of so-called local density approximation, where the energy, total energy as functional of the total density is expressed as integral over the whole space as density into the power 4/3, or integral over all elements of density with density in the power 1/3 through functional integration. This concept of density as functional, energy as a function of total density is applicable to only closed shell models where number of spins with alpha and beta projections are equal. We set up a goal that we were pursuing for last 2 lectures in their academic part, and we will complete today. There is a guarantee, but because there is only 6 slides, so we will complete the goal of expanding the concept of local density approximation into situation when there is a spin. So it will be local spin density approximation. So we do want to be able to find total energy of electronic system for the situation when number of electrons with spin projection along the axis up, alpha spins, and spin projections along down along the direction are not equal. When system practices not only singlet states but also doublets, triplets, quadruplets, and we are making all efforts with the only purpose to get hands-on understanding of the equation in the box. We already know that rho is typically used as a symbol for total density. We know what is integration, but we do not have a definition of this little psi variable. So my goal for today is very humble, is to introduce what is this psi and how we are coming to this equation. What is the motivation? Why we need to spend time and effort into this sections which may sound marginal? this is important for those of us who is going to describe magnetic materials when spins are uncompensated in any transition metals. Okay, magnetic materials, uncompensated spins. Everyone was so great in spin operators, and this probably was most challenging part in our previous lectures. We introduced the density for the situation when there are spins, and we went from a general consideration when products of orbitals prompt us 4 components of density, probability that for alpha spin, probability for beta spin, and then cross probabilities, alpha beta beta alpha, which will correspond to transversal component, which we neglect. So last time we made an effort of neglecting transversal components and focusing only on Z projection, which is needed for total energy of system with uncompensated spins in magnetic field. And we reviewed a way how to get from the density to observables, which so the energy of spin in magnetic field is expressed as magnetic field times subtraction of the spin density. So subtraction of the density with spin alpha and density with spin beta is important to evaluate interaction of this electronic system with spin to magnetic field. Okay, so I'm approaching the end of the review of the last 2 lectures. So in WASP software, in density functional theory, things are very similar to what we studied in the Hartree-Fock approach before. So if the spin is not compensated, one needs to set up needs to arrange 2 sets of orbitals, or a set of orbitals for spin alpha and set of orbitals with spin beta. The orbitals are needed in order to compose the density. The density is composed as adding together squares of the all occupied orbitals up to highest occupied. But it is important that if spins are not compensated, highest occupied orbital for spin alpha and highest occupied orbital for spin beta are not equal. If they're equal, it means we are in a closed shell singlet. If they're not equal, then we need to use this approach. And the main goal of today's meeting is to get to the boxed equation we started from, to get total energy, which is a function of the density of alpha spins and beta spins. So suppose, this is the last slide we completed before the weekend. So in case we do know the density of spins alpha and spin beta, we can add them together and integrate. So this mathematical procedure will be also a functional, the simplest possible functional. And this functional will provide summation of number of electrons with alpha and number of electrons with beta spin, which will be total number of electrons. If we subtract these 2 densities and integrate, then it will generate the subtraction of spins alpha and spin beta, which is called spin polarization, or number of unpaired spins. This number of unpaired spins, which can be like 0, 1, 2, 3, determines the spin projection, which will be then 0, 1/2, 1, 3/2. And by equation 2s plus 1 will correspond to multiplicity 1, 2, 3, and 4, singlet, doublet, triplet, quadruplet. So if anyone has questions, objections, or suggestions about this slide, please turn on microphone and express objections. I'll wait a few seconds, and if everyone is okay, I am going to go forward to material which will be new for us today. Okay? Everyone approves me to go forward?
Yes.
Okay, thank you. Yeah, thank you.
Yeah.
So, we have defined the density of alpha and beta electrons. We can construct summation of their densities, or we can construct subtraction. The units for density are 1 over volume, electron per volume, so that after integration over volume we will get number of electrons. So density is not dimensionless. Dimension of density is charge per distance square, or distance cube per volume. But mathematically, it is so much more pleasant and easier to work with dimensionless variables. Dimensionless. So if we perform a fraction, if we divide subtraction of the densities over summation of densities, we will get a parameter which is dimensionless, and it is defined in any point of space. So the name of this parameter is spin density. It is labeled by this crazy Greek letter, and this is no way my design. I'm not setting up a goal to create something new to make the class more complicated. No, it is a standard notation and standard concept used in the VASP software and any other density function software and density function literature. So spin density. When density for spin alpha and spin beta coincide, then it is 0. When they not coincide, this spin density is non-zero. I didn't prepare a special slide, but I would like to apply to your memories. So please tell me, if you can, what does appear in the VMD software, which menus appear in the first menu that appears in VMD software when someone is trying to download and plot part charge file with an orbital. So anyone is welcome to speak up, and I will give a little prompt. So when you are pushing the drop-down menus in VMD, it does ask for selection of volumetric data set. Does it bring any memories? Roger? Do you remember this keyword?
I don't remember.
Do you?
I don't.
You don't?
No.
Okay. Amir?
No, I can't remember. It's difficult for me.
Okay. When we were plotting orbitals, the I'll probably, well,
We used ISO services structure.
before oh, thank you for remembering. Before you select isosurface value, when you just download file, it asks which volumetric data set to use. Up plus down, up minus down, up or down.
Yeah, I remember.
Okay.
It asks for spin up plus spin down.
Exactly.
We choose spin up plus spin down.
Yes, yes. Now I'm going to give a comment on this. So up plus down, up minus down, and then separately up and down. So there are 4 options, but we were always selecting up plus down. So up plus down is this row alpha plus row beta. If you select up minus down, you will be plotting exactly this zeta parameter, spin density. And if you will select U up or down, you will select only row alpha or row beta. So what I'm telling right now is very much related to plotting orbitals. So let me bring your attention to a little mathematical experiment. So we do have definition of this spin density. Now, what will be if we add together spin density plus 1? So spin density is rho alpha minus rho beta divided by their sum. 1 can be represented by rho alpha plus rho beta divided by rho alpha plus rho beta. So no one can forbid me to do this little mathematical trick to represent 1 as a fraction of 2 equal things. Now, if I add together, it will be common denominator, and I will be adding together rho alpha and rho alpha, and I will be subtracting the rho beta plus rho beta and minus rho beta. So the result will be rho alpha. So by adding spin density and 1 is getting spin projection alpha divided by rho. If you multiply this 1 plus psi by total density, then it will yield the density of electrons with alpha spin. Make sense? Please?
Yes.
Okay, good. Thank you for the support. Now, the same elementary math if we take spin density and subtract 1, spin density and 1. So we have spin density as defined, and 1 is represented by, no one can forbid me to represent 1 as a fraction of equal things. So summation of alpha plus beta in the numerator and in the denominator. So this will be again a little summation of two fractions with a common denominator. Common denominator is total density. In the numerator, the alpha components will be subtracted, because here it comes with plus and here it comes with minus. And the beta component will come with minus twice. So it will be minus rho sub beta and once again minus rho sub beta. So by subtracting spin density and 1 will get projection of spin on the down direction, on the beta direction. And if we multiply left and right part by total density, one will get this rho sub beta. Make sense? Very good, very good, thank you. Now, as a next step, okay, this is just the same things, just in a better typing. The spin polarization is subtraction divided by sum. And if we add spin density and 1 multiplied by total, it will be alpha. If we put minus here, it will be beta density. Now, we do want to assume that the laws, the principles of composing total energy out of density are the same for spin alpha and spin beta electrons. This is maybe the only new information for today. The rest are just technical details. So the law of composing energy out of density is the same for alpha and for beta. If we accept this statement, then we need to practice the equation for total density once for spin alpha, once for spin beta, and then add them together. So if we accept local density approximation, then energy is integral of density to the power 4/3. If we accept that the laws of composing energy out of density are the same for alpha and beta, we will use density of alpha into power 4/3 and density of beta into power 4/3 and integrate and get the total energy, which we will call local spin density approximation. But the software that we are using and the equations that practically convert density into energy are expressed in terms of total density and spin density. So we need to make this little step. As we have discussed a couple of slides ago, the alpha component of density is summation of spin density and 1 multiplied by total. The beta density is subtraction of 1 and spin density multiplied by total. And
I have a question.
Oh, please.
So we got this local spin density from which approximation? Thomas Fermi or
No. Raju, you were asking this question, and I am skipping the derivation.
Yeah, the later approximation, am I right?
Local density approximation has a derivation that tells that density is integral of density 4/3 integrated over the whole space.
Yeah.
We are taking it as an input and trying to expand a little bit further.
Yeah, I'm just asking, sir, this approximation has been taken from the same approximation as a local density approximation.
Right.
Okay.
So we are staying within local density approximation, but we want to expand it to a broader domain of systems with explicit spin. Therefore, we add the letter S, and we call it that it is local spin density approximation. Now, the only philosophical idea is that laws of composing energy for out of density are the same for alpha and beta spin. And now we do want to convert this equation into terms of total density and spin density. So we do have an expression for composing alpha density out of spin density and total density. And then we are bringing this 4/3 power. Here we do the same. We compose beta density out of spin density and total density. And we bring up the power 4/3. So the total density into the power 4/3 can be taken out of brackets, right? And the composition of sum and subtraction of 1 and spin density can be kept inside the brackets or inside this green box. So in some sense, we are arriving to the goal of our meeting. So this equation tells how the total energy is expressed in terms of the spin density and total density. So the same thing, just maybe in better typing. So the total energy as function of alpha density and beta density is equivalent to total density in terms of total density and spin density. So on one hand, total density is alpha and beta into the power 4/3. On the other hand, it is total density in power 4/3 plus a bracket where we have summation and subtraction of spin density with 1 into power 4/3. Okay? And this expression in the brackets is dimensionless, and it represents the relative contributions of alpha and beta components. The next slide is provided here just to satisfy your curiosity. So here I am done, and you are done, with local density approximation, spin density approximation. This slide shows a little bit of the world behind, above, beyond spin density, beyond local density, beyond LDA, and of course beyond LLSDA. So the equation here does show the potential, which is functional derivative of total energy over density for one example of so-called generalized gradient approximation. So when we practically use density functional theory software, for example, it is available in Gaussian, and there is a drop-down menu when one can select different functional. And by definition, we were using B3-lib. In addition, there is a long menu of functions. There is a way to select functionally in VASP as well. And local density approximation is the simplest function, the simplest formula of converting density into total energy. There is a set of equations which will do it more precisely, and there is a competition in the world of theorists who will design a better equation. The next level of precision is when one is using not only the density, but also the gradient of density. So the gradient is the vector of derivative over x, y, and z direction. d rho dx, d rho dy, d rho dz. So in this equation, where you do see a tradition of the DFT community to give abbreviations to functionals. So this is LB94, which is by Leuven and Barentz, designed in year 94. And in its first term, it is equivalent to LDA. But then there are additional terms that provide correction. And this additional term includes different algebraic expressions of this x, which is dimensionless expression of the gradient of density. It's a vector, and it's used in square, in linear, and in the inverse exponential sign, hyperbolic sign. the derivation of these equations and approximations how they are derived are beyond the scope of this course. There is a special domain of literature and human activity for designing these equations more and more precisely. So our goal is just to get a general idea that there is a way, same as in series, one can add more terms of higher order to make this equation more precise and approach computation closer to predictions of theorems, that out of density one can find everything, including total energy and all observables. So the wording and abbreviation that we may want to memorize from today is generalized gradient approximation. So any function that uses gradient in addition to local density, in addition to simple density, is called GGA, general gradient approximation. There are 5 classes of functionals, and LDA and GGA are 2 lowest stages. There are next levels like meta GGA, hybrid functionals, which would make too much new information. So I am going to complete the lecture at this point. I will stay online to answer questions if any, and I look forward meeting you tomorrow at 5 p.m. online for the next lab.
Hi, Dr. Kelly.
Yes?
For the plotting the orbitals through the VMD, if we choose different settings, for example, the spin up minus spin down instead of spin up plus spin down, so it will influence the shape or the magnitude of the partial charge density?
Oh, yes, it will change it substantially. But let me bring slides back. There is format of lectures is not originally suited for this practical steps of computation, but I just want to show quick writing. Yes. So when we select the keyword iSpin equals 2, then the selecting part charges spin up minus spin down, only up or minus or only down will make sense. If you didn't set up this iSpin equals 2, then considerations about spin are not relevant. By definition, the value of value of this parameter is 1, which means that WASP thinks that you are trying to describe a problem where number of electrons with spin up and spin down are equal. If you know for sure that you need to go beyond this situation, if you want to practice orbitals which are specific for alpha and beta, then in the in-car one needs to add this keyword. Does it answer your question?
Yes, thanks.
Okay. Everyone is welcome to disconnect from the meeting. I do not have any new material.
Okay, thank you. Have a good day.
Thank you.
Yeah, thank you, Amir. Have a good day.
Thank you, Professor.
Thank you. Thank you, everyone.
Dr. Dimitri?
Yes?
So with the spin multiplicity, we are dealing with the charged molecules, am I right?
These two concepts and calculations are connected. Not always, but so an example. If you start with the system, with a model that has equal number of alpha and beta spins, and then you bring one electron more, if you change number of electrons, then this one electron will be unpaired, and then by it will be necessary to use this I spin equals 2. Make sense?
Yes. Yeah. So does that make that molecule charged or neutral?
Please repeat the question.
So when you unpair the electron, so the molecule will be neutral or charged?
What do you mean when I unpair the electrons? When I bring, or if I do not change, Raju, okay, let me tell something. Maybe it will answer your question. If I do not change number of electrons and I only set up the n up-down parameter, which probably you call unpaired spin.
Yes.
If I practice only this command, the number of electrons will not change.
Yes.
For example, if a system was closed shell with equal number of spins up and spin down, and you set up n up down equals 2, it will take one spin down and make it up to make the total balance of up and down equals 2. So it will just flip one spin.
Yes.
Make sense?
Yes, yes. So it doesn't affect the charge state.
Mm-hmm. Okay. Are there more questions?
No, actually, thank you very much. I was going to send you. I'm going to send you an email so that the question is. Yeah, I have more specific questions about the labs, so I'm sending you an email right now.
Okay, please. I may delay the answer because I have a grant proposal due today, but I will.
Okay.
I promise to answer it before midnight.
Okay. Okay. Sounds good then. Thank you very much.
Okay. Thank you.
Thank you. Bye bye.
Thank you. Bye bye.